Hello. Welcome once again. In this 2.5-hour tutorial, we will be going through Unreal Engine 5's basic material for beginners. This course covers the topics from basic to mid-level in material creation. Materials in Unreal Engine define the surface properties of the objects in your scene. In the broadest sense, you can think of a material as the paint that is applied to a mesh to control its visual appearance. In more technical terms, materials tell the render engine exactly how a surface should interact with the light in your scene. Materials define every aspect of the surface, including color, reflectivity, bumpiness, transparency, and so on. These calculations are done using data that is input to the material from a variety of images, textures, and node-based material expressions, as well as from various property settings inherent to the material itself. In this video series we will see how we can create materials for various meshes. So let's start creating a new material. Materials in Unreal are an asset class just like static meshes, textures, or blueprints. You can create new materials from the content browser. So right-click in the content browser. Now select Material in the Create Basic Asset section of the context menu. A material is created in the content browser. Give it a unique and descriptive name. Say Noom. Double-click the material asset to begin editing the material. The Material Editor window opens. The highlighted region is called the material graph, and this is where you will do the majority of your work while creating materials. The material graph in a new material is empty except for the main material node. Now we will see some of the material properties. When the main material node is selected, the global properties and settings for the material display in the Details panel. 3 of these settings are particularly important at the beginning of the material creation process, as they form the underlying foundation of a material and dictate how it can be used. 3 material properties control which inputs are enabled in the material. Blend mode. This controls how your material blends with the pixels behind it. Shading model. This defines how light is calculated for the surface of the material. Material domain. This dictates how the material is intended to be used. For instance, whether it is meant to be part of a surface, a light function, or a post-process material. If an input you need for your material is disabled, it is because one or more of the above properties is set incorrectly. For example, if you are trying to make a pane of glass, but the opacity input is disabled. The solution in that example is to change the blend mode to translucent. Let's see one by one. First is material domain. This defines what the material will be used for in your project. For example, surface, user interface, and post-process materials are different material domains. Then comes blend mode. This defines how the material blends with the pixels behind it. For example, opaque shaders completely occlude objects behind them, whereas translucent and additive shaders blend with the background in some way. Last is shading model. This defines how the material interacts with light. Very often your materials will simply use the default lit shading model. However, Unreal Engine includes specific shading models for things like hair, cloth, and skin, which provide context-specific inputs to make it easier to create those types of surfaces. These properties determine exactly which inputs are enabled on the main material node. In the example, opacity is grayed out because the opaque blend mode does not support transparency. If you select the translucent blend mode, the opacity input is available, and several inputs that were previously enabled are grayed out. When you create a new material, it is recommended that you configure these 3 properties first. Then comes all the available inputs on the main material node. By feeding data, by way of constants, parameters, and textures, into these inputs, you can define the surface properties of your material and create an almost infinite variety of physical surfaces. Not all inputs are required for every material, and some material types require inputs that are not visible on the main material node by default. Now start with inputs and material properties. When you change certain material properties in the Details panel, You will notice that some inputs on the main material node turn white, indicating that they are enabled, while others are grayed out. Now look at base color. Base color defines the overall color of the material. In principle, base color should represent the diffuse light reflected off a surface, minus any specular reflections, highlights. Base color defines the overall color of the material, taking in a vector 3, RGB, value where each channel is automatically clamped between 0 and 1. So holding on number 1 and left-click, gets you vector 1. Where 0 represents absolute dark or no light, and 1 represents light. And if you want to change the color, other than white, hold on number 3, and left-click, get you vector 3. Where you can change the base color as per likings. Now save the material. Without saving, the material effect will not be visible in the world. And then go to the world, and apply the newly created material onto the geometrical shape. To create another material, just duplicate the new material created, and name it differently. Then comes metallic. The metallic input controls how metal-like your surface will be. Metallic accepts any value between 0 and 1, but in a majority of cases metallic is considered an either-or property. So non-metals have a metallic value of 0. And the metals have a metallic value of 1. For pure surfaces, such as pure metal, pure stone, or pure plastic, this value will be 0 or 1, not anything in between. When creating hybrid surfaces like corroded, dusty, or rusty metals, you may find that you need some value between 0 and 1. When using metallic masks, the values in the texture should be pure black or pure white. Only use grayscale values if you specifically mean to create a blend, corroded metal, for example. The sphere on the far left has a metallic value of 1 and a roughness value of 0, so it appears to be very shiny. The sphere on the far right, however, has a metallic value of 1 and a roughness value of 1. This gives the metal a very dull look, like it has been used quite a bit. Next comes the specular. Specularity is a measure of how much light a surface reflects. The specular input takes a value between 0 and 1, and defines the extent to which a surface is reflective. The value of 0 means the fully non-reflective surface. And the value of 1 means the fully reflective, and the default value is 0.5, which represents approximately 4% reflectivity. Specular can also have an effect on the shininess of a material. Pushing the specular value closer to 1 will make the reflections and specular highlights in the material appear stronger and more apparent, while lowering that value closer to 0 will weaken the reflections and specular highlight until they are almost non-existent. Here is an example showing how the intensity of the reflections and specular highlight are affected as the specular value is changed from 0 to 1. Here is the measured specular values of some common articles. Next comes the input roughness. The roughness input controls how rough or smooth a material's surface is. Rough materials scatter reflected light in more directions than smooth materials. This value controls how blurry or sharp a reflection is, or how broad or tight a specular highlight is. A roughness of 0, i.e. smooth, results in a mirror-like reflection. A roughness of 1, i.e. rough, results in a diffuse or matte surface. Most surfaces are not uniformly rough or smooth. Roughness is a property that is frequently mapped on your objects in order to add physical variation to the surface. Scratches on metal, scuffs on a wood floor, or fingerprints on plastic are examples of materials that would require a roughness map. A roughness of 0, that is, smooth surface, results in a mirror-like reflection. A roughness of 1, that is, rough surface, results in a diffuse or matte surface. Here is this example. Roughness is shown from 0 to 1 on two different articles. Say plastic on top and metal on bottom. So you get mirror-like reflection on metal and a diffuse or matte surface of metal, and a similar effect on no metal objects. So roughness is mapped here on your objects in order to add the most physical variation to the surface. Hope this video helps you to initiate your journey into the creative world of Unreal Engine. Material instancing in Unreal Engine is used to change the appearance of a material without incurring an expensive recompilation of the material. Whereas a typical material cannot be changed without recompiling, something that must happen prior to gameplay, a parameterized material can be edited in a material instance without such recompilation. This has numerous workflow advantages, and can improve material performance. Certain types of instanced materials can even change during gameplay in response to in-game events. This allows tremendous visual flexibility in your artistic elements. To achieve this flexibility, material instancing uses a concept called inheritance. The properties of the parent material are passed to its children. Properties that are designated as parameters in the parent material are exposed to artists in the material instance editor. The relationship between materials and material instances is a hierarchical parent-child relationship. A material instance inherits all of its attributes from the parent, or master, material. For example, this is the material graph for one of the chair props found in the starter content. Any material instances created from m_chair inherit all the attributes from the graph shown above. Because they inherit their attributes from the parent, newly created material instances appear identical to the parent material when applied to objects in the level. In the image, the chair on the far left has the parent material applied while the right side three chairs use unaltered material instances. Using material instances, you can create numerous variations from a single base material. Creating material instances is a two-step process. First, create a parameterized material that you will use as the parent material for your instances. And the next step is to create a material instance constant in the content browser. You can then customize the material in the material instance editor. To make material attributes editable in a material instance, you must designate certain attributes as parameters by using parameter nodes instead of regular material expressions. Hold the S key and left-click in the material graph to place a scalar parameter. A scalar parameter is the parameterized version of a constant, and contains a single numeric value. Name the parameter roughness and connect it to the corresponding material input. Now let's check what is default value and value range. If you want to set a default value for the parameter or limit the value range, you can do so in the Details panel. For example, the roughness input accepts a value from 0 to 1. Select the roughness parameter and press Ctrl+D to duplicate the node. Rename the second scalar parameter metallic and connect it to the appropriate input. Your graph should now look like this. For the sake of demonstration, place a constant 3-vector node in your material graph. This is a standard that is non-parameterized material expression, which is often used to define the base color of a material. To convert this node into a parameter, right-click the node and choose Convert to Parameter from the contextual menu. Remember to give the parameter a unique, descriptive name like base color. You can change the color in the default value field shown above, or you can double-click the base color node to open the color picker. You cannot parameterize every material node in Unreal Engine, but the Convert to Parameter option is available from the right-click menu for any material expression that can be parameterized. Let's see how we can parameterized material example. Your material graph should now contain a vector parameter plugged into base color and 2 scalar parameters, plugged into the metallic and roughness inputs. These 3 parameters will allow you to change the color, roughness, and metallic properties of the material once you create a material instance. Click Apply in the upper left corner of the material editor to compile the material, and then click Save. Now let's create a material instance. Now that you have a simple parameterized material, you can create material instances and customize them in the material instance editor. To create a material instance, right-click your material in the content browser and choose Create Material Instance from the menu. Your material instance will derive its name from the material that you are using to create it. You can rename the material instance by selecting it and pressing F2 or by single-clicking the name field. Let's see how to editing a material instance. Double-click the material instance in the content browser to open the material instance editor. The material instance editor is the interface where you can customize material parameters to produce different-looking variations of your parent material. Now see how to adjust the material parameters. Material parameters are found in the Details panel on the right side of the material instance editor. Note that these parameters take their names from the parameter nodes in your original material graph. Use the following steps to edit a parameter. First, place a check in the box next to the parameter to enable it for editing. Next step is to type a new value in the field or left-click and drag to slide the value up and down. For vector parameters, left-click the color swatch to activate the color picker. And lastly, to reset a parameter to its default value, click the arrow icon pictured here. As you adjust parameters, the material preview will update in real-time in the material instance editor, and in the level if the material is currently applied to any actors. Note that if you change the parent material, it can completely change the appearance and properties of the material instance. The parameters you were using before may no longer be available in the new parent. So the material instancing is a powerful tool that you can use across all aspects of your project. From helping to add some variation to weapons and props, to helping artists make better use of available materials, material instances can help to streamline and unify how materials are created and used in your project. Inside of Unreal Engine 5, self-illuminated materials are known as emissive materials. In the following video, we will be covering how you set up your materials to use the emissive input as well as how you can use the emissive input to actually light the world that you are creating. The emissive color input controls which parts of your material will glow or emit light, and the brightness of the emission. Ideally, this input will receive a masked texture, mostly black except the areas that need to glow. Emissive lighting, or in UE5, emissive materials, give artists a very cheap and effective way to give the illusion that a material is casting light when it really is not. Emissive materials do this by allowing artists to push the values of the emissive input higher than 1.0, which will push the material into the HDR range, giving off a bloom effect that you might see when looking at a very bright light source. Here we have created 2 cubes for showing the comparison of a normal material and emissive material. And of course 3 walls, so as to create a darker environment. You can create new materials from the content browser. Creating emissive materials is no different than creating any other material inside of UE4. So we already have material in the name of new mat. We will make a duplicate of it and name it as emissive. Now we will apply both the material on each cubes. Let's see what is normal material. On opening the new mat, it's a 3-vector attached to the base color which gives the basic color. And some 2 vectors attached to roughness and metallic. So apply the emissive also. Both the material are the same as there is no change in the emissive material. Now go to the emissive material editor. Disconnect the base color from base color. This can be done by pressing Alt and left mouse button. And then connect the same with emissive color input. So the graph looks like this. Then save and go back and check the change in cube. Now it's glowing compared to the left one, which is basically normal color mapping. And the right one has an emissive color. Emissive materials are self-illuminating, which means that they can be used with both lit and unlit shading models. However, whenever possible, emissive materials should use the unlit shading model, as it will result in a shader that is cheaper to render. There is also no visual difference between the two different shading models in terms of how the emissive is rendered. When using the emissive input to light the world, you might find that the effect is either too subtle or too powerful. To fix this, any materials that are created should have a way to adjust the influence of the emissive light being cast into the world. Here in this case we can't change the intensity of the glow, so we have to add one scalar parameter. So press 1 and left mouse button. And convert the same into parameters. Name it emissive strength. Now on the left-hand side, you will see default values for emissive strength. Set the default value as 0, and max value as 200. With the material expression nodes now labeled and filled in, it is now time to start to wire everything together. The most important part to make sure to wire up correctly is the emissive input, as without that, no emissive will work. Now add one multiply node onto the graph. Connect one node to emissive strength and other to the base color. And connect the out execution pin to the emissive color. When completed, your material graph should look like the following. Now that the material is wired up, make sure to compile and save the material by pressing both the Apply and Save buttons at the top of the material editor. Now that the material has been compiled and closed, find the material in the content browser and then right-click on the material and choose the Create Material Instance option to make a material instance from the emissive material. To change a parameter, you must first enable the parameter by using the left mouse button to click on the checkmark box that is next to the name of the parameter you want to enable. After clicking, a checkmark should be added to the box and both the name and the input area will no longer be grayed out. Now it is just a matter of inputting the values that you want to use and saving the material instance. In the shader that we created above, this parameter was called emissive strength. By increasing the emissive strength, you will increase the amount of light that is cast into the world when building light. Decreasing the emissive strength, you will lessen the amount of light that is cast into the world. In the images, you can see how increasing the emissive strength increases the emissive effect on the world. Here in this examples of what happens when we set the emissive strength to a value of 0 on the left, 1 in the middle, and 25 on the right. You can input textures, numbers, or a combination of both into the emissive input. What you input really depends on the needs of the material. If the emissive material is just to simulate light, then using a numeric value instead of a texture is the way to go. However, if you want to simulate lights on an object, using a texture as a emissive mask is the way to go, as you can define in the mask texture exactly which parts should be illuminated. In the example above, we used emissive masking as we used a texture to define where the emissive parts of the material should be. In the texture parameter, choose any texture of your choice. We have taken Alisplay logo on it. You can add various input node and connect the same, so the final graph would look like this. Connect the wires and your final graph should look like this. Now save. And go back to the material instance. Here change the value of emissive strength and observe the lightness. Here the whole thing is glowing. We can make the body dim and have only logo glowing by change the base color. In order to see the effects the emissive will have on the world, you need to build your level lighting. If you do not do this, your changes will not be seen. This also means that whenever you make a change to the emissive material, you will also need to rebuild lighting to see the changes. You can also change the color of the emissive by changing the emissive color vector parameter. Here are some examples of what changing the color of the emissive looks like. In this video we will look at material blend modes and how they affect the rendering of a material. Blend modes describe how the output of the current material will blend over what is already being drawn in the background. Put more technically, it allows you to control how the engine will combine this material, source color, with what is already in the frame buffer, destination color, when this material is rendered in front of other pixels. Blend mode options are found in the Details panel with the rest of the base material properties. This document uses a sphere placed between the camera and a wall to demonstrate the various blend modes. By changing the blend mode on the sphere material, you can see how the object blends with the pixels behind it. The opaque blend mode is the most straightforward, and probably the one you will use most often. It defines a surface through which light neither passes nor penetrates. This is perfect for most plastics, metals, stone, and the larger percentage of other surface types. The masked blend mode is used when you need to selectively control visibility in a binary, on-off, fashion. For example, consider a material that simulates a chain link fence or grate. You will have some areas that look solid while others are invisible. Such materials are perfect for the masked blend mode. A masked material graph is shown below, with a black and white striped texture plugged into the opacity mask input. White parts of the mask are rendered, while black parts are invisible. There are no intermediate levels of opacity when using a masked material. Here is that material from the camera's perspective. It is important to keep in mind the difference between transparent and not rendered. A transparent surface, such as glass, still interacts with light in the form of reflections, specularity. Pixels that are culled in masked mode simply do not draw. You will not see any reflections in those areas. If you want to retain reflections or specular aspects, you would do well to use the translucent blend mode, or consider making a layered material. Further, since these features don't render in the masked area, they aren't calculated at all, leading to performance savings on the GPU. When using masked blend mode, you need to pay special attention to the opacity mask clip value property. This property holds a 0 to 1 scalar value which controls what value of the opacity mask texture will be used as a cutoff point, beyond which all darker pixels will not render. In the example above, the material has its two-sided property set to true, checked, which is why you can see the inside of the box. Also, despite the interactive example shown here, the opacity mask clip value property is not designed to be changed at runtime. The translucent blend mode is used for objects that require some form of transparency. This differs from the masked blend mode in that it allows varying levels of translucency. This blend mode works by taking in an opacity value or texture and applying it to the surface such that black areas are completely transparent, white areas are completely opaque, and the varying shades of gradation between result in corresponding transparency levels. In the example, a black to white gradient is plugged into the opacity input, resulting in a sphere that is fully transparent at the top of the mesh and gradually reaches full opacity at the bottom. An important consideration when using translucent materials is that they do not currently support specularity. This means that you will see no reflections along the surface. However, such reflections can be faked using a cube map in a node network similar to this. The cube map texture is simply added on top of the base color. The additive blend mode simply takes the pixels of the material and adds them to the pixels of the background. This is very similar to the linear dodge, add, blend mode in Photoshop. This means that there is no darkening. Since all pixel values are added together, blacks will just render as transparent. This blend mode is useful for various special effects such as fire, steam, or holograms. As with the translucent blend mode, this blend mode does not respect specularity, i.e. reflections. The additive nature of the blending probably means you will not use it anyway, but it is possible to simulate a reflection-like effect using the CubeMap method shown above in the translucent section. In the image below, a second sphere was added to the scene. Note that where the two spheres overlap, the pixels are added together and therefore brightened. One drawback of additive materials is that they are often difficult to see against light-colored backgrounds. A side view of the spheres demonstrates this. A solution is to use the alpha composite blend mode instead, with a texture that has a pre-multiplied alpha channel. This improves saturation and visibility in bright scenes. The modulate blend mode multiplies the value of the material against the pixels of the background. The behavior is very similar to the multiply blend mode in Photoshop, and produces a darkening effect. In the graph above, the material shading model is set to unlit and the blend mode to modulate. A constant 3 vector is plugged into the emissive input to define the surface color. Notice again that with multiple spheres, the pixels that overlap are multiplied together and become darker. The modulate blend mode is best suited for certain particle effects, but care must be taken as it does not support lighting or separate translucency. Alpha composite is used in materials that have textures with pre-multiplied alpha, meaning the RGB color channels were pre-multiplied by the alpha channel before the image was stored. The alpha composite blend mode is a useful alternative to the additive or translucent blend modes for brightly colored particles and VFX. Compared to additive blending, alpha composite materials have better visibility and maintain more color saturation against light-colored backgrounds. Bright regions of the material are less likely to blow out to pure white due to additive buildup. The video below shows an alpha composite material with an opacity parameter. At low opacity levels the material works more like an additive blend, whereas at opacity levels 0.5 and higher it resembles translucent blending, creating an interesting transitional effect near the edges of the mask. The alpha hold-out blend mode lets you hold out the alpha of a material, punching a hole through the objects directly behind it in view space. The following image shows the camera and scene layout for an alpha holdout implementation. First the camera. Second a static mesh in the foreground acts as the hole-punching object. The alpha holdout material is applied to this mesh. This material must use the unlit shading model. Third the receiving surface, which you intend to punch a hole through, is placed behind the alpha holdout object. In this case, a brick wall. The material on the receiving surface must use either the translucent, additive, modulate, or alpha composite blend modes. An alpha holdout material cannot act upon an opaque material. Last one is the background of the scene, which will be visible through the hole. From the camera's perspective, you will see a transparent hole through the receiving surface, making the objects behind it visible. Because the alpha holdout material is on a separate static mesh asset, you can easily move it around in editor or animate it in game. When creating certain surface types such as water or glass, you need the ability to make the surface not only see-through, but also give the surface a sense of depth and color. In the real world, these properties are referred to as transparency or opacity, and the two often used interchangeably to describe the same thing. In Unreal Engine, transparency and opacity have two distinct meanings. Transparency is used to define whether or not a surface can be seen through. Opacity is used to define degree to which a surface transmits light. In other words, the opacity value determines how transparent or opaque, how see-through, see-through, a surface is. In this video you will learn everything you need to know about how to use transparency in your Unreal Engine materials. Transparency is the term used to describe a surface's ability to block or allow the passage of light. For example, a brick is an object that has no transparency. Stained glass transmits some but not all light, and therefore it is a surface with transparency. Opaque and masked blend modes also use opacity when using one of the subsurface shading models. Opacity is mostly used for translucent, additive, and modulated materials. The opacity input is enabled when the translucent blend mode is selected, typically for translucent, additive, and modulated materials. In Unreal Engine, Transparency works by assigning each pixel an opacity value between 0 and 1. The image shows opacity values increasing from 0 to 1 on a static mesh. So, 0.0 represents a completely transparent material. When opacity is 0, the surface allows all light to pass through. And 1.0 represents a fully opaque material. The surface is fully opaque, meaning it blocks 100% of the light that hits it. And finally, fractional values between 0 and 1 produce semi-transparent or translucent materials. That means there is partially see-through. You can also define opacity with a grayscale texture. The image demonstrates how a texture can help define which parts of a mesh should have transparency and how transparent they should be. The texture is a gradient that goes from black at the bottom, or fully transparent, to white at the top, or fully opaque. The areas in the middle have a varying degree of opacity based on how close to black or white the pixel in the texture is. You can set up transparent materials using the following steps. First, right-click in the content browser and then select Material from the Create Basic Asset section of the context menu. Name the material Transparent Material and then open it by double-clicking the material thumbnail in the content browser. The material editor opens. Add the following material expressions to your graph. 1 vector parameter and 1 scalar parameter. Rename the vector parameter node to base color and give it a color value. Rename the scalar parameter to opacity and give it a default value of 0.5. Click in the background of the material graph to display the material properties in the Details panel. Under the Material section, change the blend mode from opaque to translucent. Now that the blend mode has been correctly set, connect the output of the vector parameter node into the base color input on the main material node. Click Apply and then Save in the Material Editor toolbar to compile the material and save the asset. Find the transparent material asset in the content browser. Right-click the thumbnail and select Create Material Instance in the context menu. Once the material instance is created, left-click and drag the material instance onto the mesh and release the left mouse button to apply it to the mesh. Open the material instance by double-clicking on it in the content browser. In the Material Instance Editor, override the opacity amount parameter by checking the box next to the parameter name. Once enabled, you can adjust the value of opacity amount to change how transparent the object will be. Now we will try getting some texture into the material. Objects that make use of transparency can display scene reflections if the following options are set. However, keep in mind that having a lot of translucent materials that have reflections enabled could cause performance issues. Now, inside the material graph, select the opacity amount parameter and duplicate it twice by pressing Ctrl+D on the keyboard. Rename the new material expression nodes to metallic and roughness. Set the default value of the metallic material expression to 1.0 and set the default value of roughness to 0. Then connect each material expression node to the corresponding input on the main material node. In the Details panel under the Translucency category, change the lighting mode from volumetric non-directional to surface forward shading. When completed, your material graph should look something like this. Now, click Apply and save the Material Editor toolbar and then close the Material Editor. You should now be able to see reflections on the spheres in your level. By adjusting the parameters of the material instance, you can make the transparency have extremely different looking results. With the thin transparent shading model and material expression, You can accurately represent tinted and colored transparent materials, such colored glass and plastics. This shading model enables white specular highlights with correctly tinted background color for transparent surfaces. Add a thin translucent material expression to the graph and connect a constant 3-vector or a vector parameter to the input. This node controls color tint of the transparent surface. Configure the material with the following properties in the Details panel. Change the shading model to thin translucent. Opacity mask is similar to opacity, but is only available when using the masked blend mode. Unlike the opacity input, the opacity mask does not allow for partial or intermediate transparency levels. When using an opacity mask, regions of the material are either fully visible, or fully invisible. This makes it a good solution when you need materials that define complex solid surfaces such as wire mesh, chain link faces, and fances, so on. We have seen in earlier videos that the masked blend mode only has pixels that are completely opaque or completely transparent. You can use a grayscale texture or a single channel from a texture to use as a mask. It is important to keep in mind the difference between transparent and not rendered. A transparent surface, such as glass, still interacts with light in the form of reflections, specularity. Pixels that are culled in masked mode simply do not draw. You will not see any reflections in those areas. When using masked blend mode, you need to pay special attention to the opacity mask clip value property. This property holds a 0 to 1 scalar value which controls what value of the opacity mask texture will be used as a cutoff point, beyond which all darker pixels will not render. Further, since these features don't render in the masked area, they aren't calculated at all, leading to performance savings on the GPU. Clip value lets you set a threshold when the pixel will be opaque or transparent. The opacity mask clip value property allows you to set the value at which clipping takes place for textures that have thin sections. Those areas will disappear in the distance as the mipmap forces the white out of the image or channel. Adjusting clip value will allow you to adjust when that occurs. For example, if the opacity mask clip value is set to 0.5, pixels with a value greater than 0.5 on the opacity mask become fully opaque. Pixels with a value lower than 0.5 on the opacity mask become fully transparent. The main material node of the material graph is where all of the material expression nodes that are added to the material graph will end up being connected to. The results of what is input into the main material node is what will be displayed when the material is compiled and applied to objects in-game. Materials are created using a specialized coding language called High-Level Shading Language or HLSL. Inside Unreal Engine 5, the material expression nodes that are used to create materials contain small snippets of this HLSL code. The inputs on the main material node are the last stop in a UE5 material graph. Whatever combination of material expression nodes is connected to the inputs on the main material node is what determines the overall appearance of the final material when it is compiled and used in your level. The main material node with default inputs are here. Each input on the main material node has a unique effect on how the material will look and perform. A white-colored input means that input will have an affect on the material, while grayed-out input will have no affect on the material. By default, the main material node does have some of its inputs grayed out. To enable inputs or disable inputs on the main material node, the following properties have to be modified in the Details panel of the material. Blend mode. Shading model. Let's see what are material inputs. Each input on the main material node defines a single unique aspect of the appearance and surface properties of your material. For example, if you connect a constant 3 vector to the base color input and give it a value of 1, 0, 0, you can make the material red. This material graph only explicitly defines a single aspect of the material, its base color. However, the overall appearance of the material is the collective result of all the enabled inputs in the main material node. Enabled input pins are white on the main material node, and disabled inputs are grayed out. Inputs that do not receive any data from material expressions in the graph simply revert to their default values. For example, even though there is nothing plugged into metallic, specular, or roughness, these properties still contribute to the appearance of the material. Metallic defaults to 0, non-metallic. Specular defaults to 0.5. Roughness defaults to 0.5. Therefore, a material with those values plugged into metallic, specular, and roughness looks exactly the same as the one shown previously. Note that the preview render does not change when default values are connected to the main material node. By changing the values, you can alter the appearance and surface properties of the material. In the third image, the roughness value is changed from 0.5 to 0.07, and the material appears more polished. Changing the values in the constant 3 vector to 0, 0, 1 makes the base color blue instead of red. UE5 uses a physically based rendering (PBR) workflow for materials, meaning materials closely approximate the way surfaces interact with light in the real world. To create materials effectively, it is important to understand exactly how each input affects the final material. Let's understand how to enable and disable inputs. Some of the input pins in the main material node are enabled by default, while others are disabled. The following properties in the Details panel determine which inputs are enabled. Material domain, blend mode, shading model. Modifying any of these 3 material properties can change the inputs that are enabled and disabled in the main material node. In the middle example, changing the blend mode from opaque to translucent enables the opacity and refraction inputs. It also disables any inputs that are not used by translucent materials. On the far right, selecting the clear coat shading model enables the inputs for clear coat and clear coat roughness. You must select the main material node to access these properties in the Details panel. Please note, the nodes connected to disabled inputs are ignored. When switching between blend modes or shading models, some inputs may become disabled. Material expressions remain connected to disabled inputs, but are ignored when the material is compiled. In this example, a constant value was connected to opacity. The blend mode was changed from translucent to opaque, causing the opacity input to become disabled. The constant node remains connected to the opacity input, but the cable and input are grayed out to indicate that the input is disabled. Nodes connected to disabled inputs do not affect the compiled material in any way. When the main material node is selected in the material editor, the Details panel displays a list of all editable properties relating to how the material can be used. As demonstrated above, properties like blend mode and shading model directly influence which inputs are enabled in the main material node. Other sections let you modify how the material interacts with specific platforms or rendering features. Here is a brief breakdown of what each section in the main material node Details panel does. Description first is physical material. This allows you to specify what type of physical material is used for this material. Next is material. This is where you will spend most of your time when editing materials. The material section is where you can change the material domain, blend mode, and shading model along with many more options. Physical material mask. An array of physical material maps to be used for this material. Translucency. This is where you can adjust how translucency in this material will function. Please note that this is only editable if the material blend mode is set to translucent. Translucency self-shadowing. This is where you can adjust how translucent self-shadowing looks and behaves. Please note that this is only editable if the material blend mode is set to translucent. Usage. This is where you set what type of objects this material will work with. Usage flags are usually set automatically by the editor. However, if you know that this material is supposed to be used with a certain object type, make sure you enable it here to avoid any future mistakes. Mobile. This is where you set how this material should work when used on a mobile device like a smartphone. Forward shading. Per material overrides for when the forward shading renderer is in use. Group sorting. Allows you to change the order of parameter groups in your material. Post-process material. This is where you define how this material should work with post-process and tone mapping. Please note that this is only editable if the material domain is set to post-process. Refraction. Properties to change the refraction mode and refraction depth bias. Light mass. This is where you can adjust how this material will interact with light mass. Previewing. Change the static mesh used to preview the material in the material editor viewport. Import settings. A selection of import data types and options relevant to the selection for use with this material. Now let's see how to use the main material node. Inputs on the main material node work exactly like any other material expression or function in the material graph. To connect a material expression to an input in the main material node, first left-click the output pin of a material expression and drag the mouse to an input pin on the main material node. Then, release the left mouse button over the input pin when the green check icon appears. Previewing and applying materials. The main material node is the endpoint of a UE5 material graph. The information that you pass into the inputs on the main material node is what ultimately determines the appearance of the material. As you connect material expressions to the main material node, the preview in the material editor viewport updates continuously so you can evaluate your changes and make sure you are getting the desired results. Material expression node with the value of 0.5 to the roughness input on the main material node. At this point, you can now begin to adjust both the values of the constant material expression and the constant 3-vector material expression to change the look of the material. You can also connect different material expressions and combinations of material expression into the other inputs. For example, see what happens when you try and input something into the emissive or normal inputs on the main material node. Finally, make sure to press both the Apply and Save buttons. Refraction is the term used to describe the change in direction of a light wave due to a change in its transmission medium. In other words, when light comes in contact with certain surfaces, like water or glass, the light is bent or redirected because those surfaces affect the speed at which light travels through them. You can see a classic example of refraction by dipping a pencil into a bowl of water. The pencil will appear to bend or change directions at the spot where the pencil intersects the water. The illustration below shows how refraction works. X shows the true physical position of the pencil when it is dipped in water. The light rays from the submerged portion of the pencil are refracted at the air-water interface, changing speed and direction. From the camera's perspective, the pencil appears to bend at the surface of the water, with the tip appearing at position Y instead of its true position X. Let's see what is index of refraction or IOR. Index of refraction or IOR is an optical measurement that describes the extent to which light is bent, or refracted, when it enters a particular material. Index of refraction can be measured, and real-world values for common surfaces are well known. When creating refractive materials in Unreal Engine, it is best to use real-world IOR values to give your materials a better sense of realism. The table below lists measured IOR values for some common surface types. Now let's use refraction in materials so we have a material made, in the name of refraction material. In the Details panel, change the blend mode from opaque to translucent. Expand the translucency section and change the lighting model from volumetric non-directional to surface translucency volume. Changing these settings will enable the refraction pin on the main material node. When completed, your details panel properties should look like this. Now add some material expression nodes, 4 constants, and convert 2 into scalar parameters. And name them as opacity and other 1 IOR. Begin wiring up the material. Change the constant value flowing into base color and metallic to 1. For parameters opacity, give it a default value of 0.3 and connect it to the opacity input. Parameter IOR as in its default value to 1.52, which is basically the IOR of glass. Your material graph should look like this. Find the refraction material asset in the content browser. Right-click on the thumbnail and select Create Material Instance from the context menu. Drop a few objects into your scene to test the material. Drag the refractive material _inst asset from the content browser onto the meshes in your scene. Double-click on the refraction material _inst to open it in the Material Instance Editor. Enable the IOR parameter by checking the box next to the parameter name. Once enabled, you can set the IOR to different values to simulate different surface interaction. The video below shows how the refraction changes when the value is set to 1.0, air, 1.33, water, 1.52, glass, and 2.42, diamond. Refraction and normal maps. Adding an option to use a normal map with your refractive material will yield some very interesting results, especially in areas where the normal map has a lot of interesting detail. Follow the steps below to modify the refractive material created above so that it works with normal maps. First, find a normal map to use. For this example, T_water_n from starter content was used. However, any normal texture will work. Open the refraction material asset and drag the normal texture from the content browser into the material graph. Right-click on the normal map texture sampler and select Convert to Parameter. Rename the parameter normal map and connect it to the normal input on the main material node. By parameterizing the texture, you give artists a way to override it in a material instance without editing the parent material. In the Material Instance Editor, you should now see the normal map parameter listed under Global Texture Parameter Values. You can override the normal map by enabling the parameter and choosing a different texture from the drop-down menu. By changing the normal map, you can change the material's refraction in interesting ways. Here are some examples using only the normal maps you can find in the Textures folder of the starter content. Now let's see how refraction and movement together. Combining refraction with motion is a key component in many types of materials. Ripples on water are one example, but the technique is similarly useful in a lot of VFX materials such as heat haze, distortion from a large explosion, or energy effects. The graph below shows one way to add organic-looking motion to the normals. Duplicate the normal map, and connect them to the A and B inputs on a lerp node. Add 2 Panner material expressions to the graph and connect them to the UVs of the normal map textures. Change the values in the Panner nodes to add motion to the textures. Making some of the values negative moves the texture in the opposite direction, and is a good way to create organic, random-looking motion. Here are the values used for the 2 Panners in this example. In its current state it resembles an oily, metallic-looking fluid, but with some modifications it could be the basis for a water material. Adding refraction to your materials is a great way to get realistic-looking results for translucent materials like glass and water. Remember to consult the chart at the top of the document and use correct IOR values for the type of surface you are trying to simulate. The constant expression outputs a single float value. It is one of the most commonly used expressions and can be connected to any input, regardless of the number of channels the input expects. For instance, if you connect a constant to an input expecting a 3-vector, the constant value will be used for all 3 elements. When supplying a single number, it can be useful to collapse the node using the small triangle icon in the description area. R specifies the float value the expression outputs. You can quickly create a constant node by holding the 1 key and left mouse click in the graph area of the material editor. Nest is constant 2-vector. The constant 2-vector expression outputs a 2-channel vector value, in other words, 2 constant numbers. R specifies the float value of the red, first channel of the vector the expression outputs. G specifies the float value of the green, second channel of the vector the expression outputs. The constant 2-vector is useful for modifying texture coordinates, as they are 2-channel values as well. You can quickly create a constant 2-vector node by holding the 2 key and left mouse click in the graph area of the material editor. Third is constant 3-vector. The constant 3-vector expression outputs a 3-channel vector value, in other words, 3 constants numbers. An RGB color can be thought of as a constant 3-vector, where each channel is assigned to a color, red, green, blue. R specifies the float value of the red, first channel of the vector the expression outputs. G specifies the float value of the green, second channel of the vector the expression outputs. B specifies the float value of the blue, third channel of the vector the expression outputs. You can quickly create a constant 3-vector node by holding the 3 key and left mouse click in the graph area of the material editor. Fourth is constant 4-vector. The constant 4-vector expression outputs a 4-channel vector value, in other words, 4 constants numbers. An RGBA color can be thought of as a constant 4-vector, where each channel is assigned to a color, red, green, blue, alpha. R specifies the float value of the red, first channel of the vector the expression outputs. G specifies the float value of the green, second channel of the vector the expression outputs. B specifies the float value of the blue, third channel of the vector the expression outputs. A specifies the float value of the alpha, fourth channel of the vector the expression outputs. You can quickly create a constant 4-vector node by holding the 4 key and left mouse click in the graph area of the material editor. Next is distance cull fade. The distance cull fade expression outputs a scalar value that fades from black to white and can be used to fade an object in once it comes within the cull distance. It should be noted that it does not fade the object out. This network will cause the object to fade in, instead of popping, once the camera comes within the cull distance. Next is time. The time node is used to add the passage of time to a material, such as a panner, cosine, or other time-dependent operation. Ignore pause if true. Time will continue to march on even if the game is paused. Period if true, this will be the amount at which to wrap around time. On mobile materials, this will perform the period computation on the CPU at full precision, whereas on the GPU it will run at half precision, potentially having issues on periods longer than a minute. The network described in the image above would create a material that would change over time, constantly exhibiting a sinusoidal transition between white and black. If you enable period, setting period to 0 will effectively stop the transition and 1 will be as if period was false. Setting the number closer to 0 will make the material change at a more rapid pace. Next is two-sided sine. The two-sided sine expression is useful for flipping the normal on backfaces of two-sided custom lighting materials to match the functionality of Phong. +1 for front faces, -1 for back faces of a two-sided material. Next is vertex color. The vertex color expression is the access point for the material to the outputs of color modules affecting mesh. There are really an infinite number of ways one could use the colors from a vertex color material expression. For this setup, we are going to keep things relatively simple and just multiply the colors into an existing material. This allows us to have the original texture in place, but to tint it with the Mesh Paint tool. In order to make this paintable, we need to get the vertex color material expression worked into the network. The base material network looks like this. This material has been desaturated a bit, giving us more room to add color using the Mesh Paint tool. To get our vertex colors worked into the material, we simply need to intercept the base color connection and multiply it by a vertex color expression's RGB value, like so. Next is particle color. The particle color expression ties into the current color of a given particle based on any per-particle color data defined within Cascade. This must be plugged into the appropriate channel, emissive color. In this example, you can see where the particle color expression is providing color to the particles as defined within the particle system. In this video we will see what are the expressions that perform actions on texture coordinates or output values that can be used as, or to modify, texture coordinates. Actor position world space outputs vector 3. That is, RGB, data representing the location of the object with this material on it in world space. In this example, you can see that actor position WS is being fed directly into the base color of the material. As a result, each of the spheres with the material applied to them show a different color as they are moved to different locations in 3D space. Note that the result of the actor position WS node is being divided by 1600 to create a nice blend in color, rather than a pop. The camera world position expression outputs a 3-channel vector value representing the camera's position in world space. The preview sphere changes color as the camera rotates. The object orientation expression outputs the world space up vector of the object. In other words, the object's local positive z-axis is pointing in this direction. Now moving the sphere changes the color. One side it's positive with specific color. Opposite side it's negative with black color. The object position WS expression outputs the world space center position of the object's bounds. For example, this is useful for creating spherical lighting for foliage. So in this example, the sphere is in central location with 0, 0, and for x, y and z location. Now moving the sphere changes the color. One side it's positive with specific color. Opposite side it's negative with black color. The object radius outputs a value equal to the size of a given object in unreal units. Scaling is taken into account and the results can be unique for each individual object. In this example, both meshes are receiving this material in which the object radius is fed into diffuse. The object radius output is being divided by 512 to provide a more meaningful visual result. Now in image left where object radius is not fed, both the mesh seems to have different material in terms of size of the tiles. In right image, the object radius is fed. The same material has been fed and the tiling is same. The panner expression outputs UV texture coordinates that can be used to create panning, or moving, textures. SpeedX specifies the speed to pan the coordinates in the U direction. Speedy specifies the speed to pan the coordinates in the V direction. Now let's check the inputs. Coordinate takes in base UV texture coordinates. The expression can then modify. Time takes in a value used to determine the current panning position. This is usually a time expression to provide a constant panning effect, but a constant or scalar parameter can be used as well to set a specific offset or to control the panning through matinee or blueprints. Panner generates UVs that change according to the time input. The coordinate input can be used to manipulate the UVs generated by the panner node. So in another example, the Paneer node along with the texture coordinator has been used to generate some basic water-like material, with some rippling effects. The rotator expression outputs UV texture coordinates in the form of a two-channel vector value that can be used to create rotating textures. Center X specifies the U coordinate to use as the center of the rotation. Center Y specifies the V coordinate to use as the center of the rotation. Speed specifies the speed to rotate the coordinates clockwise. Now let's see the inputs. Coordinate takes in base UV texture coordinates. The expression can then modify. Time takes in a value used to determine the current rotation position. This is usually a time expression to provide a constant rotation effect, but a constant or scalar parameter can be used as well to set a specific offset or to control the rotation through matinee or blueprints. The texture coordinate expression outputs UV texture coordinates in the form of a two-channel vector value, allowing materials to use different UV channels, specify tiling, and otherwise operate on the UVs of a mesh. Coordinate index specifies the UV channel to use. U tiling specifies the amount of tiling in the U direction. V tiling specifies the amount of tiling in the V direction. Unmirror U if true. Undo any mirroring in the U direction. Unmirror V if true. Undo any mirroring in the V direction. The vertex normal WS expression outputs the world space vertex normal. It can only be used in material inputs that are executed in the vertex shader, like world position offset. This is useful for making a mesh grow or shrink. Note that offsetting position along the normal will cause the geometry to split apart along UV seams. The pixel normal WS expression outputs vector data representing the direction that pixels are facing based on the current normal. In this example, pixel normal WS is fed into base color. Notice how the normal map is used to give the per pixel result. Here in this example, the snow on rock is cited with pixel normal and vertex normal, and both the example show how based on pixel and vertex the color or texture variation happens. The world position expression outputs the position of the current pixel in world space. To visualize, simply plug the output into emissive. Common uses are to find the radial distance from the camera to a pixel, as opposed to the orthogonal distance from pixel depth. World position is also useful to use as a texture coordinate and have unrelated meshes using the texture chord matchup when they are near each other. Here is a basic example of using world position to planar map. Without the absolute world position wired, the two meshes shows different. However, when the absolute world position is wired, the mesh seems one, and there is a continuity of same material sheet. The world position offset input allows a material to manipulate the vertices of a mesh in world space. This is useful for making objects move, change shape, rotate, and a variety of other effects. World position offset is often used for subtle, ambient animation. The above network causes the sphere to grow and shrink along its vertex normals with a sinusoidal period of 1 second. When using world position offset to expand your object beyond its original bounds, keep in mind that the renderer still uses those original bounds. This means that you may see culling and shadowing errors. You may go into the properties of a mesh and set its scale bounds property to compensate, though this has a draw on performance and may lead to shadowing errors. The world position offset category contains special functions for manipulating vertices of a mesh via world position offset. These functions can be chained together for additive effects. The following is a list of all the functions underneath the world position offset category. The simple grass wind function applies a basic wind operator to foliage, giving the ability to specify a weight map and wind strength. This is a non-directional wind that just gives a very general movement to foliage. This should be the last WPO node you add. The spline thicken function serves as a way to make very thin polygons look thicker at render time. This is perfect for cables, hair, grass, and other such objects. Objects using this function should be extremely thin and should be imported with remove degenerate triangles disabled. The camera offset function is great to assist with depth sorting, as it allows you to move an object in camera space, either toward or away from the camera. The object pivot point function returns the object's pivot point in world space. This is not compatible with the pixel shader. The object scale function returns the object's XYZ scale together and separately. This is not compatible with the pixel shader. The pivot axis function creates a common pivot location on arbitrary axes. This is helpful for creating flag motion. Instead of using a single pivot point near the top of the flag, use a shared Z point and unique X and Y location data to create a more realistic connection along the object's width. The rotate about world axis _cheap function cheaply rotates objects around world axes. Input the angle you would like to use and attach the output to world position offset. The static mesh morph targets function unpacks morph target data that was added into a via 3ds Max's morph packer max script. The wind function provides separate outputs for wind strength, speed multiplied by time, and a normalized wind vector. In this video we're going to be looking at the various math nodes available in the Unreal Material editor and give a few examples of how they might be used within our shaders. The add expression takes two inputs, adds them together, and outputs the result. If you pass values with multiple channels, each channel is added separately. For example, if you pass RGB color values to each input, the R channel of the first input is added to the R channel of the second input and the result is stored in the R channel of the output. The G channel of the first input is added to the G channel of the second input and the result is stored in the G channel of the output, and so on. Both inputs must have the same number of values, unless one of the values is a single constant value. In that case, each channel of the multi-channeled input is added to the single float value, and the result is stored in a separate channel of the output value. Add is often used to brighten, darken colors or to offset UV texture coordinates. The subtract node takes in two inputs, subtracts the second input from the first, and outputs the difference. If you pass values with multiple channels, each channel is subtracted separately. For example, if you pass RGB color values to each input, the R channel of the second input is subtracted from the R channel of the first input and the result is stored in the R channel of the output. The G channel of the second input is subtracted from the G channel of the first input and the result is stored in the G channel of the output, and so on. Both inputs must have the same number of values, unless one of the values is a single constant value. In that case, each channel of the multi-channel input has the constant value subtracted from it, and the result stored in a separate channel of the output value. The multiply expression takes two inputs, multiplies them together, and outputs the result. When you pass color values as input, the results are similar to the results of the multiply layer blending mode in Photoshop. If you pass values with multiple channels, each channel is multiplied separately. The divide expression takes two inputs, divides the first input by the second, and outputs the result. If you pass values with multiple channels, each channel is divided separately. The 1- expression takes an input value, x, and outputs, 1 - x. This operation is performed per channel. Examples: 1 - of 0.4 is 0.6, 1 - of 0.2, 0.5, 1.0 is 0.8, 0.5, 0.0. 1 minus of 0.0 minus 0.4, 1.6 is 1.0, 1.4 minus 0.6. When the input colors are in the range 0, 1, 1 minus has the same effect as what is commonly called invert, that is, 1 minus returns the complementary color that when added to the input will produce white. The power expression takes two inputs, a base value, base, and an exponent, exp. It raises the base value to the power of the exponent and outputs the result. In other words, it returns base multiplied by itself expressed times. Example usage. If the colors you pass to power are in 0, 1, power can behave as a sort of contrast adjustment, where very bright values are dimmed slightly, but darker values are decreased drastically. ABS is an abbreviation for the mathematical term, absolute value. The ABS expression outputs the absolute, or unsigned, value of the input it receives. Essentially, this means it turns negative numbers into positive numbers by dropping the minus sign, while positive numbers and 0 remain unchanged. The absolute of a value just means to take the value and make it positive, ignoring any negatives. I.e. ABS, minus 4, equals 4. This is occasionally useful when creating masks using complex math or for creating a bouncing motion from a sine wave. Examples. ABS of minus 0.7 is 0.7. ABS of minus 1.0 is 1.0. ABS of 1.0 is also 1.0. The clamp expression takes in values and constrains them to a specified range, defined by a minimum and maximum value. A minimum value of 0.0 and maximum value of 0.5 means that the resulting values will never be less than 0.0 and never greater than 0.5. Now check the properties. Clamp mode selects the type of clamp to be used. Min default takes in the value to use as the minimum when clamping, only used when the min input is unused. And max default takes in the value to use as the maximum when clamping, only used when the max input is unused. Now understand the inputs. Min takes in the value to use as the minimum when clamping, and max takes in the value to use as the maximum when clamping. Examples. Clamping an input range of 0.0 to 1.0, 0.3 with min 0.0 and max 1.0 yields 0.3. Clamping 1.3 with min 0.0 and max 1.0 yields 1.0. The component mask expression allows you to select a specific subset of channels, R, G, B, and or A, from the input to pass through to the output. Attempting to pass a channel through that does not exist in the input will cause an error, unless the input is a single constant value. In that case, the single value is passed through to each channel. The current channels selected to be passed through are displayed in the title bar of the expression. Examples. Component mask with an input of 0.2, 0.4, 1.0, and the G channel will produce an output of 0.4, which appears as a 40% bright grayscale value when used as a color vector. Ma and min, two comparison nodes which return the maximum or minimum of the two inputs per pixel. Useful for creating strange masks, such as seen here, or for creating pseudo-random motion. For example, on a graphic equalizer shader you could take the max of two out-of-phase sine waves to create semi-realistic pseudo-random movement. The seal expression takes in values, rounds them up to the next integer and outputs the result. Examples. Seal of 0.2 is 1.0. Seal of 0.2, 1.6, is 1.0, 2.0. The floor expression takes in values, rounds them down to the previous integer and outputs the result. Examples. Floor of 0.2 is 0.0. Floor of 0.2, 1.6, is 0.0, 1.0. The frac expression takes in values and outputs the fractional portion of those values. In other words, for an input value, x, the result is x minus floor of x. The output value will range from 0 to 1, inclusive on the low end, but not the high end. Examples. Frac of 0.2 is 0.2. Frac of minus 0.2 is 0.8. Frac of 0.0, 1.6, 1.0 is 0.0, 0.6, 0.0. In this example, the frac node is converting time into a series of repeating 0 to 1 progressions, causing the color to fade via the lerp from green to red, then snap back to green, repeating indefinitely. These three nodes are similar. Ceil or ceiling takes an input and returns the next integer rounding up. Floor does the same but rounding down, and frac or fraction just returns the floating point part of the value. Note the black in the floor example and the white in the ceil, due to rounding down and up. Frac is the most useful here, generally returning repeating values from something like time or sine, but floor and ceil have their uses too. The if expression compares two inputs and then passes through one of three other input values based on the result of the comparison. Both compared inputs must be single float values. Let's understand the description of each input. Input A takes in a single float value. Input B takes in a single float value. Inputs A greater than B takes in the values to output. If the value of A is greater than the value of B, inputs A equals B takes in the values to output. If the value of A is equal to the value of B and inputs A is greater than B, or if if this pin is unconnected. In this example, the if expression takes in a height map, and outputs either red or green, based on whether the height falls, under or over a value of 0.45. It compares two input values A and B, and returns a different input value. If A is greater than B or if A is smaller than B, there is also a special case for A equals B, which is basically never really needed in shader writing. It defaults to A equals greater than B if this pin is unconnected. The linear interpolate expression blends between two input values based on a third input value used as a mask. This can be thought of as a mask to define transitions between two textures, like a layer mask in Photoshop. The intensity of the mask alpha determines the ratio of color to take from the two input values. If alpha is 0.0, the first input is used. If alpha is 1.0, the second input is used. If alpha is between 0.0 and 1.0, the output is a blend between the two inputs. Keep in mind that the blend happens per channel. So, if alpha is an RGB color, alpha's red channel value defines the blend between A and B's red channels independently of alpha's green channel, which defines the blend between A and B's green channels. Now we're talking. This node just takes two inputs and blends between them, based on an input value, 0 to 1. Values of 0 will result in input A and values of 1 input B. This is a real workhorse of a node in shader writing, being used all the time for any manner of things. The append vector expression allows you to combine channels together to create a vector with more channels than the original. For example, you can take two individual constant values and append them to make a two-channel constant 2 vector value. This can be useful for reordering the channels within a single texture or for combining multiple grayscale textures into one RGB color texture. This node is basically the opposite to the mask node we covered earlier. It takes two inputs and outputs them combined, such as in the example where we're combining three scalar values into a vector 3 or color. Another indispensable node when working with scalars and vectors. The sine expression outputs the value of a sine wave over the input range of 0, 1, and the output range of -1, 1, both repeating. The difference between this and the output of the cosine expression is the output waveform is offset by 1/4 of the period. Most commonly, this is used to output a continuous oscillating waveform by connecting a time expression to its input, but it can also be used to create ripples in world space or screen space, or any other application where a continuous, smooth cycle is needed. Now let's see what is input period. Specifies the period of the resultant wave. In other words, this is how long one full oscillation takes to occur, or the time between each successive crest or each successive trough in the waveform. For example, in the image above, the period is 1 second. The cross-product expression computes the cross-product of two 3-channel vector value inputs and outputs the resulting 3-channel vector value. Given two vectors in space, the cross-product is a vector that is perpendicular to both of the inputs. The max expression takes in two inputs and outputs the higher of the two. When you use this node with color inputs, the result is similar to the lighten layer blending mode in Photoshop. In the example above, A is 0, and B is 1, therefore, 1 inch, white, is the resulting base color. The min expression takes in two inputs and outputs the lower of the two. When you use this node with color inputs, the result is similar to using the darken layer blending mode in Photoshop in the example above. A is 0, and B is 1, therefore, 0 inches, black, is the resulting base color. The normalize expression calculates and outputs the normalized value of its input. Normalized vectors, also called unit vectors, have an overall length of 1.0. This means each component of the input is divided by the total magnitude, length, of the vector. Examples: passing either 0, 2, 0, or 0, 0.2, 0, through normalize will output 0, 1, 0. Passing 0, 1, minus 1, through normalize will output 0, 0.707, minus 0.707. The only special case is an all-zero vector, which will be unchanged. The round expression rounds the input value to the nearest whole number. If the fractional part of the input value is 0.5 or greater, then the output value is rounded up. Otherwise, the output value is rounded down. Examples: a value of 1.1 will be rounded down to a value of 1. A value of 1.4 will be rounded down to a value of 1. A value of 1.5 will be rounded up to a value of 2. A value of 1.85 will be rounded up to a value of 2. Hi, welcome once again. In this video we will see what are the material expressions that deal with depth of the pixel being rendered. The depth fade expression is used to hide unsightly seams that take place when translucent objects intersect with opaque ones. Now see the inputs. Opacity, this takes in the existing opacity for the object prior to the depth fade. Next is fade distance, this is world space distance over which the fade should take place. Once the effect is in place, you will notice that the cube which was fully gray, now becomes transparent at the lower side. Now the transparency is equal to the unreal units that is entered in the fade distance. This effect will come when the translucent objects intersects with opaque ones. Here we have added two scalar constant to both the inputs of depth fade. We will modify these scalar figs and check the effect. So we have already seen the sharpness of edges when the fade distance is set to 0, and quite diffused when the fade distance has some numbers. Now let's see how we can modify it in terms of colors in the fade distance zone. And again, just by changing the various channels and main material node, the depth fade color can be modified, as per your desire and requirement. Here in this example the fade distance zone has a different color altogether. So again the color can be played with by some modification in the material main node. The pixel depth expression outputs the depth, or distance from the camera, of the pixel currently being rendered. This expression supports positive values and not negative ones. This is because the renderer relies on the conservative depth optimization to maintain good performance on modern hardware. This has the added benefit that if depth can move away from the camera, hardware depth rejection can be reused from the vertex shader output. Otherwise, allowing pixel depth offset to move towards the camera could cause objects to poke through anything, and the pixel shader would have to run the pixel shader for all pixels regardless of whether they are occlude without pixel depth offset or not. In this example, the material network has been applied to the floor. Notice how the linear interpolation blends between the two colors as the floor recedes beyond 2048 units. A power expression was used to boost the contrast between the two colors and yield a more meaningful visual result. Now in the example what we can is a sudden change in color, which might not look appealing or desirable. So we can do some modification and have the effect more smooth and some blended colors reflecting in final result. So here in this example we have a plane with the same material added. So both the edges are of the same color at a certain distance. Now on changing the distance the color changes based on the pixels and the transition is smooth from original color to final color. Still the mesh will take up more than one color at a time, depending on the distance you have entered. So after adding component mask, in another example, the transition to final color has different effect. Here the whole mesh is one color, and that color is basically the blend or transition of initial color to final color. The scene depth expression outputs the existing scene depth. This is similar to pixel depth, except that pixel depth can sample the depth only at the pixel currently being drawn, whereas scene depth can sample depth at any location. Only translucent materials may utilize scene depth. In this example, we have applied the material network to a translucent sphere. Notice how the scene depth node is reading the pixels behind the sphere, rather than the ones on its surface. The resulting normalized depth is linear in the 0.0 to 1.0 range. Hi, welcome once again. In this video we will see what is Fresnel material expressions. Oftentimes when creating a film or cinematic, you need a way to better highlight the silhouette of a character. This lighting technique is often referred to as rim lighting or edge lighting, and involves adding additional lights to help better distinguish the character's silhouette from the background. While this works quite nicely for film, adding additional lights to any 3D scene adds extra complexity that can quickly become difficult to manage. Unreal Engine offers a solution to this by allowing artists to simulate the same basic effect using the material of the character. This way, the artist has more control over the look and feel of the effect and can even use it for things like adding lighting to an unlit object to save on performance. Fresnel is the term used to describe how the light you see reflects at different intensities based off of the angle you are viewing it from. In Unreal Engine, the Fresnel material expression node calculates a falloff based on the dot product of the surface normal and the direction to the camera. When the surface normal points directly at the camera, a value of 0 is output, meaning there should be no Fresnel effect happening. When the surface normal is perpendicular to the camera, a value of 1 is output, meaning the full effect of the Fresnel should be taking place. The result is then clamped to 0 and 1, so you do not have any negative color in the center. The following image demonstrates this concept. In the middle of the sphere, where the 0 is, you will see that there is no Fresnel effect. This is because the camera is pointing directly at the surface normal. As the surface normal becomes more and more perpendicular to the camera, or getting closer and closer to the number 1, the Fresnel effect becomes more and more visible, and this is the type of behavior we want. When searching for the Fresnel material expression, you will find that there is a Fresnel under Utility and one under VectorOps. While these two material expressions have the same name and do the same thing, they do differ in how you set them up for use. First, check Fresnel utility. The Fresnel that is found under Utility is the one that is used in this how-to and is the simplest one out of the two to set up and use. So the exponent in controls the falloff of the Fresnel effect. The base reflect Refraction in specifies the fraction of specular reflection when the surface is viewed from straight on. Setting this to a value of 1 effectively disables Fresnel, and the normal is, where you can input a normal to affect the way the Fresnel effect is rendered. This property cannot be set by supplying either a normal map or a vector 3 input. You have two options for adjusting the values for the Fresnel material expression. Select the Fresnel material expression in the material graph and then input values via the Details panel. Add constant or scalar nodes to the material graph and then hook them up the respective inputs. When using a normal map, make sure to add a transform expression node. This will transform the normal map from tangent space into world space. If this transform is not performed, your normal map might not influence the Fresnel the way you intend. Now let's check the Fresnel vector ops. The Fresnel that is found under vector ops is a highly customizable version of Fresnel that allows you to affect many different aspects of how the Fresnel is rendered. However, this added functionality has its drawbacks, as incorrect settings or setup could lead to artifacts or errors in how the Fresnel effect is rendered. This node should only be used if the Fresnel that is under utility does not yield the results you're looking for. So let's see how we can use the Fresnel in material. Add some base node and when completed, your material graph should look like this. Once this has been done, the parameter can then be edited. For example, if you enable the Fresnel parameter, you can increase or decrease the effect the Fresnel has on the surface. Remember that inputting bigger numbers into Fresnel_express will push the Fresnel effect closer and closer to the edges, and lower numbers will bring the effect closer to the center. Here is an example of what happens to the Fresnel when the Fresnel expo value is to different values. Notice how as the number increases, the Fresnel effect is pushed closer and closer to the edges of the mesh, like in the following example. Now let's see how you can add normal map and defile the Fresnel effect. If you input a normal map into the normal input of the Fresnel, you will see that you can affect the surface in a number of very interesting ways. This is because of the normal map's influence over the surface normal. As we learned before, the Fresnel works by checking to see if the surface normal is perpendicular to the camera or not. If it is perpendicular to the camera, then the Fresnel effect will take place. On a smooth sphere, this means that the Fresnel will only take place at the edges of object. However, when a normal map is introduced, we change the surface normal to no longer be smooth, allowing the Fresnel effect to happen in places that it normally would not if the surface normal had been smooth. For a visual example of what is going on, take a look at the following image showing the effect the surface normal has on the Fresnel. On the left is what the Fresnel node will output with a flat surface normal. Now take a look at the right-hand side. In this image, a normal map was input which drastically changes the surface normal. Because the surface normal is no longer flat everywhere, you get more of the Fresnel being displayed. In the image below, we can see how different normal maps can affect the Fresnel in different ways. The material that was used to create the images above was the same material that was created before, but with the following modifications made. A new 2D texture sampler was added and plugged into the normal input. The Fresnel material expression can also be supplied with a normal map that can affect the way the Fresnel is rendered. This is particularly useful if you want to use the Fresnel to display something like an energy shield on a material but still have that material look normal when the shield is not active. To achieve this using the material above, the following things need to be done. First, start by updating the translucency lighting mode by changing it from volumetric non-directional to surface translucency volume. Then change the base color and roughness parameters. Next, change the normal input so that it uses T_brick_clay_n, which can also be found in the starter content. Next, search for a transform expression node in the palette and add it to the material graph. Make sure that it is set to transform from tangent to world space. Now connect the old normal map texture node into the input of the transform node and connect its output into the normal input on the Fresnel node, and when completed, your material should look something like this. Notice how the bricks look like they have nothing to do with the Fresnel. You can even take this one step by adding a multiply and constant expression node and then using that to control the intensity of Fresnel effect. Here is how that would look when added to the material from above. By adjusting the constant that was added, you can control how the Fresnel affects the surface. Setting the number to 0 turns off the effect, and setting it to anything else will gradually reveal the effect, like in the example below. Let's see other uses for Fresnel. Due to the way Fresnel works, it can be used to do other things besides just rim lighting. Here are some examples of using the Fresnel node to do other things than just rim lighting. Input blending. You can use the Fresnel as the alpha for a lerp to control how inputs to the lerp are combined together. Adding Fresnel to a material is a great way to help better illuminate a character's silhouette or to help show an energy shield special effect. Remember that Fresnel works based off of viewing angle and surface normals, so if you want to add some interesting detail to the Fresnel, try using a normal map that has a little random noise in it. Also, do not forget that you can use Fresnel material expression to help blend between two different inputs, which is very handy for visual effects like fire or smoke. In this video, we will see what are material expressions that perform operations on vector input values. First is append vector. The append vector expression enables you to combine data channels together to create a vector with more channels than the original. For example, you can take two individual constant values and append them to make a two-channel constant 2-vector value. Append vector is also useful for reordering the channels within a single texture or for combining multiple grayscale textures into one RGB color texture. Let's check the inputs. Input A that takes the values to append additional data to, and B. This takes in the values that will be appended to A, for example. Append vector works in order of input, meaning the data in input B is appended to the end of the data in input A. In the example below, there are two separate append operations. First, 0.2 and 0.4 are appended together, resulting in a two-channel vector, 0.2, 0.4. In the second append node, a constant value of 1 is appended to the end of 0.2, 0.4. The final result is a three-channel vector, 0.2, 0.4, 1. In this example, it is used as an RGB value to define the base color of the material. Next vector is component mask. The component mask expression enables you to select a specific subset of channels, R, G, B, and/or A, from the input to pass through to the output. Attempting to pass a channel through that does not exist in the input will cause an error, unless the input is a single constant value. In that case, the single value is passed through to each channel. The current channels selected to be passed through are displayed in the title bar of the expression. Select the component mask expression in the material graph, and use the checkboxes in the Details panel properties to choose which channels are allowed to pass through to the output. Let's check the properties. R. If R is checked, the red, first, channel of the input value is passed through to the output. Next is G. If G is checked, the green, second, channel of the input value is passed through to the output. Then B. If B is checked, the blue, third, channel of the input value is passed through to the output. And lastly, A alpha. If A is checked, the alpha, fourth, channel of the input value is passed through to the output. The example below shows a component mask with an input of 0.2, 0.4, 1.0. Only the G channel is enabled in the Details panel, so the node outputs a value of 0.4. This appears as a 40% bright grayscale value when passed into the material's base color input. Next vector is cross product. The cross product expression computes the cross product of two 3-channel vector value inputs and outputs the resulting 3-channel vector value. Given two vectors in space, the cross product is a vector that is perpendicular to both of the inputs. Let's check the input. The A takes in a 3-channel vector value, and B takes in a 3-channel vector value. Example usage. Cross product is often used to compute directions which are perpendicular to two other directions. Next vector is derive normal z. The derive normal z expression derives the z component of a tangent space normal given the x and y components, and outputs the resulting 3-channel tangent space normal. The inputs x_y takes in the x and y components of the tangent space normal in the form of a 2-channel vector value. Next vector is dot product. So what is actually a dot product, and how can it be used? Well, dot product multiplies two vectors together, and it then sums up the results of those multiplications. So let's say, for example, you have x multiplied by x, y multiplied by y, z multiplied by z, and then you add the resulting numbers. The dot product expression computes the dot product, which can be described as the length of one vector projected onto the other, or as the cosine between the two vectors multiplied by their magnitudes. This calculation is used by many techniques for computing falloff. Dot product requires both vector inputs to have the same number of channels. The input A takes in a value or vector of any length. The input B takes in a value or vector of the same length as A. Next is transform. Transform. The transform material expression converts a 3-channel vector value from one reference coordinate system to another. By default, all shader calculations in a material are done in tangent space. The vector constants, camera vector, light vector, and so on are all transformed to tangent space before being used in a material. The transform expression allows you to transform these vectors from tangent space to the world space, local space, or view space coordinate systems. Additionally, it enables world space and local space vectors to be transformed to any of the other reference coordinate systems. Subsurface scattering is the term used to describe the lighting phenomenon, where light scatters as it passes through a translucent or semi-translucent surface. Unreal Engine offers a special shading model, called subsurface. Subsurface is used specifically for materials that need this interaction like skin or wax. The ability to render realistic-looking human skin is a must for any modern video game engine. To fulfill this need, Unreal Engine now offers a shading method specifically for skin or wax-like surfaces called Subsurface Profile. While the Subsurface Profile shading model has similar properties to the Subsurface shading model, its key difference is in how it renders. The following guide will walk you through all you need to know about how to use subsurface scattering in your materials, and what a subsurface profile is and how you can use them in your work. First, we will see how to enable the subsurface shading model. Enabling a material to use the subsurface shading model can be done a few steps. First, create a new material by right-clicking in the content browser and then selecting material from the Create Basic Asset list. Once created, make sure that you name the material. Next, open up the material by double-clicking on it with the left mouse button. Now with the material open, we need to change the material's shading model from default lit to subsurface. The material is now ready to be used as a subsurface material. Continuing with our material from above that has subsurface scattering enabled, let's set up a basic material so that we can see the subsurface scattering in action in a level. We need to place down some material expression nodes so that we have something to work with. For this example, we are going to be adding 2 vector parameters and 2 scalar parameters. Once the material nodes have been named and filled in with the correct data and connected the material nodes to the main material node, you should have something that looks like this. Now that all the nodes have been connected, make sure that you compile the material by pressing the Apply button. Once compiled, you should have something that looks like this. Now let's check the working with the subsurface material. Now that the subsurface material has been applied, it is time to tweak the settings of the material instance. First is opacity controls. In the current setup of our subsurface material, the opacity input controls the amount of light that we want our object to scatter. A setting of 0 will allow all light to scatter, where a setting of 1 will let no light scatter. 0.5 in the middle image and 1.0 in the image on the right. Notice as the numbers go from 0 to 1, the amount of light we see passing through the object becomes less and less. Next is subsurface color value. While you can adjust the amount of subsurface scattering that happens via the opacity input, you can also adjust this using the value slider in the color picker. For example, setting the opacity to a value of 1.0 and setting the subsurface colors value from white to black will effectively turn off subsurface scattering like in the example below. If you do the opposite of this, adjusting the value slider in the color picker so that it is now in the white, you will re-enable subsurface scattering like in this example. Here is an example of adjusting the value in real time. The amount of subsurface scattering influence is affected. Now here in this example we have eliminated all the light source except for the flames and the statue. And we keep on moving the flame. While the opacity does help to get rid of a lot of the scattered light, you might notice that there is still some subsurface scattering happening. To get completely rid of the effect, you are also going to have to adjust the value of the subsurface color. In the current setup of our subsurface material, the opacity input controls the amount of light that we want our object to scatter. A setting of 0 will allow all light to scatter, where a setting of 1 will let no light scatter. The following example shows the back of the statue with the opacity value set at 0 in the image on the left, 0.5 in the middle image and 1.0 in the image on the right. Notice as the numbers go from 0 to 1, the amount of light we see passing through the object becomes less and less. The clear coat shading model can be used to better simulate multi-layer materials that have a thin translucent layer of film over the surface of a standard material. Additionally, this shading model can be used with either metal or non-metal surfaces. It was specifically designed to model this second class of smooth-colored films over a non-colored metal. Some more examples of clear coat materials include lacquer clear coats, used on furniture, for example, or colored films over uncolored metal, such as with car paint or soda cans. Create a new material in the content browser with a name of clearcoat and then double-click on it to open it up. Select the main material node and in the Details panel under the Material section, change the following options. Shading model to clear coat. The clear coat shading model enables two new material inputs on the main material node. First is clear coat. Amount of clear coat layer, 0 acts like the stand, and shading model, 1 is the full clear coat model. This is useful for masking. Next is clear coat roughness, roughness for the clear coat layer. Our approximation is accurate for small values. Very rough clear coat layers are supported but will not be very accurate compared to their real-world counterparts. Add 4 scalar parameter expression nodes to the material graph and give them the following names: base color, then metallic, then clear coat, and lastly clear coat roughness, and give them values, and then connect them. After connecting, the editor should look like this. Here we have added even a texture sample to make the clear coat effect more evident. In the image on the left, clear coat value is 0. While the surface without the clear coat is interacting with the lighting, the light is only affecting the surface in one direction. In the image on the right, clear coat value is 1. You will notice that more light is now interacting, producing an alternating pattern of highlights and shadows with a sense of directionality. This makes the surface appear flat and smooth. Let's see what the gradient mapping actually means, and the basic concept behind it. Given a black and white input image and a colored gradient, all black and white values are mapped into the equivalent color values of the given gradient. So it applies a gradient of color to your image depending on the tones in the image. Where the image is darker, the colors at the left of the gradient are applied, and where the image is lighter, the colors at the right of the gradient are applied. Let's take a look as to what this actually means in this example, using the gradient map adjustment layer in Photoshop. When we apply our colored gradient to a black and white image of a flame, we get the result shown below. The gradient functions produce procedurally generated gradients made from texture coordinate expressions. They save memory over having to create a texture-based gradient. Now let's understand what are the gradient functions in Unreal. First is radial gradient exponential. The radial gradient exponential function uses UV channel 0 to produce a radial gradient, giving the user the ability to adjust the radius and offset the center point. There are two inputs: UVs, which is a vector 2, which allows the ability to control where the gradient resides and how much it covers the 0 to 1 space. Center position, which is a vector 2. This is a 0 to 1 based offset for the position of the gradient center. Here only R and G channel works, out of RGB channel. B channel have no effect here. Radius, which is a scalar, this controls the size of the radial gradient from its center. The default of 0.5 puts the edges of the gradient at about the edge of the texture space. Density, which is also scalar. Density adjusts the hardness of the resultant gradient generated by the function. The higher the number means the sharper the gradient. Invert density, which is a Boolean. Invert density inverts white into black and black into white for the gradient. So here the gradient material instance has been created, and to check the various effects. Next is diamond gradient. The diamond gradient function uses UV channel 0 to produce a radial gradient, giving the user the ability to adjust the falloff rate of the gradient. Let's check the inputs. Falloff, which is a scalar. Falloff boosts gradient contrast by controlling how quickly the gradient shifts from white to black. Next is linear gradient. The linear gradient function uses UV channel 0 to generate a linear gradient in either the U or V direction, depending on which output is used. Let's check the inputs. First is U gradient. This outputs a linear gradient in the U direction. Next is V gradient. This outputs a linear gradient in the V direction. Okay, here we have added a scalar and multiply node. And then connected to the base color. Now we will change the blend mode to masked from opaque. And then connect multiply output to the opacity mask. After adjusting the single vector amount, the black portion is visible, and the white portion is masked out. On changing the scalar amount, the amount of black portion changes. But no more gradient is visible. So in spite if gradient applied, it's masked. Now select the gradient main node and go down and make Dither enabled. On enabling the Dither, you can see the gradient type masked effect. But it's still not smooth. To have it smooth, change the blend mode to translucent, from masked. And connect the output node of the multiply node to opacity from the opacity mask. Here we are. Now the gradient mode is quite smooth. Let's add some colors to the gradient and make it more visible. Here are some other examples, where linear gradient is used with add node. Where the new color is gradient with the white. With lerp note, two different colors are gradient along with the white color. And with subtracting note, the new effect is evident. Although any random material can be used with a landscape actor, the material system inside Unreal Engine 5 provides some landscape-specific material nodes that can help improve the textures for your landscape. In this tutorial, we explain how these material nodes function, and how you can use them in your landscape materials. You can modify materials for use with landscapes the same way you modify other materials, in the material editor. So let's create a new landscape material, name it landscape and open it. So let's start with landscape-specific material nodes. Inside of the material editor, there are 6 specific nodes that can be used with the landscape system. You can find all these nodes in the palette menu, under the landscape category. First is Landscape Layer Blend node. The Landscape Layer Blend node enables you to blend together multiple textures or material networks so that they can be used as landscape layers. The Landscape Layer Blend uses an array to store information about the landscape layers. To add layers to this array, select the plus sign icon. When you add multiple layers to the Landscape Layer Blend node, the layer names populate in the Landscape Layer Blend node. First is Layers. This contains the list of layers the node contains. You can add layers by clicking the plus icon, plus sign. Second is Additional Layers. These are what additional layers look like when they are collapsed. Third is Layer Name. This is the unique name that you give the layer. The layer name corresponds to the layer name used in Paint mode in the Landscape tool window. Fourth is Blend Type. This is either LB_alpha blend, LB_height blend, or LB_weight blend. Fifth is Preview Weight. This is the weight value for the layer to preview the blending in the material editor. Sixth is Const Layer Input. This is for supplying a numeric value as a color to use in case you do not want to use a texture. This is mainly used for debugging a layer if there is an issue. Seventh is Const Height Input. This is for supplying a numeric value as a height in case you do not want to use a texture. Let's see the details of the Layer Blend node inputs and outputs. First is Layer that's as, layer name, for example Layer Soil. Each layer adds an input for the layer to blend together. This input is only available after layers are added and named in the Details panel. Second Height that's as, layer name, for example Layer Grass. This is where you supply a height map to blend with. This input is only visible on layers that have their blend type property set to LB_height blend. Last one is in labeled output. Landscapes use weight blending rather than alpha blending, so the blend factors for all layers at any location will add up to 1.0. Alpha blending is useful because it does not depend on order, so you can paint any layer at any time. Additionally, when you use alpha blending the alpha layer weight is increased, while other existing layer weights are decreased. However, the disadvantage to using alpha blending is that when one layer is painted to 100%, the weight value for all other layers will be 0%. This is shown when using the Paint tool to remove a layer that is already at 100%. Because the other layers are at 0%, the tool has nothing available to replace the 100% layer you are removing, so it appears as if the layer was not changed. Now see the various landscape layer blend types. The Landscape Layer Blend material node has 3 different blend modes that you can choose from. Each different layer blend type is used when you are trying to achieve a different result. First is LB Weight Blend. Use if you have layers coming in from an external program, like World Machine, or if you wanted to be able to paint any layer independent of one another without worrying about layer order. Next is LB Alpha Blend. Use if you want to paint in detail and if you want a defined layer order. For example, painting snow over rock and grass will occlude them, but erasing snow will reveal rock and grass beneath it. Last is LB Height Blend. This is the same as LB_weight blend but also adds detail to the transition between layers based on a height map. This allows, for example, dirt to appear in the gaps between rocks at the layer transition point, instead of just smoothly blending between rock and dirt. Here is an example of the LB Height Blend in action. As you can see, the dirt appears in the gaps between rocks at the layer transition point. This way you get a nice transition where layers meet. Now let's see what's blending layers. When using certain combinations of layer blend modes, you could end up with black spots all over your landscape where different layers meet. This problem is especially prevalent when using the LB_height blend mode for multiple landscape layers. LB_height blend works by modulating the blend factor, or weight, for the layer using the specified height value. When you have multiple layers painted on an area and they all are set to LB_height blend, it is possible that all the layers painted in a particular area will simultaneously have a zero height value, so the desired blend factor for each layer becomes zero. Because there is no implicit or explicit ordering, the result will be black spots because no layers will have any contribution to that area. The situation is worse when you are blending a normal map, because it results in a normal value of 0, 0, 0. Which is not valid and will cause rendering problems with the lighting. The solution to this problem is to use LB_alpha blend for one of the layers like in the example below. In the left image, all layers are LB_height blend, causing some areas to be black. On the right, the red 1 layer has been changed to use LB_alpha blend, which solves the problem. Below is an example of the properties of the landscape layer blend node for all the layers being blended together. Make sure to note how the soil layer has its blend mode set to LB_alpha blend while the other layers have theirs set to LB_height blend. This is to stop the issue mentioned above, having black spots where layers meet, from happening. If you need to delete a layer, click the drop-down arrow to the right of the layer's element number to open the menu, and select Delete. Next expression is Landscape Layer Chords node. First is Mapping Type. The E-Landscape Chord mapping type that specifies the orientation to use when mapping the material, or network, to the landscape. Second is Custom UV type. This is the mapping place to use on the terrain. The custom UV type outputs the UV coordinates to map the material to the landscape based on the given property values. Third is mapping scale. This applies uniform scaling to the UV coordinates. Fourth is mapping rotation. This applies the rotation in degrees to the UV coordinates. Fifth is mapping pan, U. This applies the offset in the U direction to the UV coordinates. Sixth, mapping pan, V. This applies the offset in the V direction to the UV coordinates. Seventh is in labeled output. This outputs the UV coordinates to map the material to the landscape based on the given property values. Next expression is landscape layer switch node. The landscape layer switch node allows you to exclude some material operations when a particular layer is not contributing to a region of the landscape. This allows you to optimize your material by removing calculations that are not necessary when a particular layer's weight is 0. Let's go through the various properties of landscape layer switch node. First is parameter name. This is the unique name that you give to the parameter. Second is preview used. This, if checked, uses a preview. Third, layer used. This is when the layer specified in the node's properties is in use by the current region of the landscape. Fourth is layer not used. This is when the layer is not used by the current region of the landscape and has a weight of 0. Fifth is in labeled output. This is either the layer used or layer not used inputs, depending on whether or not the layer contributes to the particular region of the landscape. Next expression is landscape layer weight node. The landscape layer weight expression allows material networks to be blended based on the weight for the associated layer obtained from the landscape the material. The weight for this layer is used as the alpha value for blending the two input networks. Let's check the properties of landscape layer weight node. First is parameter name. This is the unique name that you give to the parameter. Second is preview weight. This is the weight to use for preview purposes in the material editor. Third is const base. Here you can specify a base color here that you would like for your landscape to have. Fourth is base. This is the network to blend this layer with. This is generally the result of any previous layer blending, but can be empty if this is the first layer. 5th is layer. This is the network to blend together to create this layer. 6th is in labeled output. Outputs the result of the blending between the base and layer inputs based on the layer weights of the layers involved. Last expression is landscape visibility mask node. The landscape visibility mask node removes visible parts of your landscape, so you can create holes in your landscape to, for example, create caves. The properties of landscape visibility mask node is in labeled output. This outputs the visibility mask properties. Make sure the output is connected to the opacity mask slot of your material and that the material's blend mode is set to masked. Otherwise the node may not work correctly. Welcome once again. In this video we will see how to create landscape material and how to add some materials to landscape, so that it better resembles something that we see in the real world. But before you do this, you need to first set up some folders to organize the content that you create and migrate into your project. Start by creating a new folder called Landscape in your project's content folder. Then inside the Landscape folder, create the following 3 folders: Materials, then Resources, and lastly Textures. When completed, you should have something that looks like the following. Now we will look for some landscape textures. Now that we have the folders in place, it is time to migrate some textures from the Landscape Mountains Learning project so that we have some textures to work with. This project can be found under the Learn tab in the Epic Games Launcher. You can find the textures located in the following folder located in the Landscapes Content Example project. Then, Game, then, Example Content, then, Landscapes, then, Textures. The textures that you will be migrating over from the Landscape Content Example project are as follows. First TLS Grass 01D, second TLS Grass 01N, third T Full Grass D, fourth T Full Grass N, fifth T Ice Noise N. Once you have the textures migrated over, make sure they are placed in the Textures folder. Now start creating the landscape material. Creating a material for our landscape can be done in the following steps. Right-click in the content browser and select Material from the Create Basic Asset list. Name the newly created material something that will allow you to easily find it, like Landscape Material for example. With our new landscape material created, open up the material by double-clicking on it inside of the content browser. It is time to start adding nodes inside of the material editor. The first node that you are going to want to create is a Landscape Layer Chords UV node. This node will help to generate UV coordinates that will be used to map the landscape material to the landscape actor. The quickest way to find nodes specific to landscape is to search for them in the Materials palette box using landscape as the keyword. The next material nodes that we are going to add are going to be for the textures for the ground's base color and normal maps. For the snow, we are just going to use a vector parameter, that's as v plus left click. That uses an off-white color. To make sure that no metallic information is used, a constant, that's as 1 plus left click, of 0 is used and plugged into the metallic input. Finally, for the roughness, we set a scalar parameter, that's as s plus left click, so that this value can be tweaked via a material instance. To add the texture sample nodes for the various textures, select the desired texture in the content browser and then press T plus left click in the material editor's graph to create the node. First, TLS Grass 01DD stands for diffused map. Second, T Full Grass D. Third, TLS Grass 01NN stands for normal map. Fourth, T Full Grass N, and lastly, T Ice Noise N. After the material nodes have been added, and the landscape chords connected to the textures UVs, it is time to add and set up the landscape layer blend node. The landscape layer blend node allows for the blending of layers via weight blending, height blending, or alpha blending. Weight blending uses each layer's painted weight to determine which to display. We use weight blending where we want two surfaces to blend seamlessly into each other, such as rock into sand. Height blending uses the same weight information along with an additional height value taken from the texture sample's alpha channel and is best used when one material needs to clearly sit on top of another, such as the grass and snow sitting on top of the soil layer. Finally, alpha blending uses the painted weight information with an alpha layer to determine the final result. The following table shows what textures are associated with which layer name and what blend type they use. When you first place down a landscape layer blend node, it will be blank like in the image below labeled 1. To add layers, you need to select the node in the material graph and then in the Details panel, click on the plus icon that is in between the word elements and the trash can icon. How many textures you are using will determine how many layers you will want to have. Now let's modify the layer blend base color first. TLS Grass 01D, set layer name as soil. Blend type as weight blend. And preview weight as 1.0. Then T full grass D, set layer name as grass, blend type as height blend. And preview weight as 0.0. And snow as a vector 3, set layer name as snow. Blend type as height blend. And preview height as 0.0. Now let's modify the layer blend normal. First TLS Grass 01N, set layer name as soil. Blend type as weight blend. And preview weight as 1.0. Then T full grass N, set layer name as grass, blend type as height blend. And preview height as 0.0. And lastly snow noise as a vector 3, set layer name as snow. Blend type as weight blend. And preview weight as 0.0. Once the layer blend nodes have been set up, it is time to connect the texture maps to them. Height blended materials will have both a layer connection and a height connection to accommodate the need for the additional height information. Finally, make sure that you connect the landscape chords to the UVs of each of the texture samples. When completed, your node network should look like this. Now let's see how to paint the landscape materials. With the landscape material created, it is time to apply the material to the landscape and begin using the paint tools. With the landscape material selected in the content browser, select the landscape in the world. Then in the Details panel, expand the landscape section and look for the landscape material input. Apply the material to the landscape using the Use Selected Asset from the content browser arrow icon. You can also drag the material asset from the content browser to the Details panel and drop it on the landscape material input. When completed, you should have something that looks like this. If you see black lines in your landscape, they come from having unbuilt lighting. If you rebuild your level's lighting, the black lines will go away. Now that the landscape material is applied, it is almost time to start painting, but before we can do that, we must first create and assign 3 landscape layer info objects. If you try to paint before you assign the landscape layer info objects, you will get the following warning message. You need to create 3 landscape layer info objects, one for each texture that you want to paint. Here is how you do it. First, make sure that you are in landscape paint mode. Then in the landscape panel, under the target layers section, you should see 3 inputs labeled soil, grass, and snow. To the right of the names, there is a plus sign icon. Clicking that will bring up another menu that will ask what type of layer you would like to add. For this example, pick the weight blended layer, normal, option. When you select the weight blended layer, normal, option, you will be prompted with a pop-up box that is asking you where you want to save the newly created landscape layer info objects. Select the resources folder that is under the landscape folder and then press the OK button. Once you have completed the first one, repeat the same process for the other 2. You should have something that looks like the following. Now with the landscape layer info objects created and applied, we can begin to paint our landscape. The main tool that you will use for applying textures to your landscape is going to be the paint tool. To apply a material to the landscape, press and hold the left mouse button to apply whatever you have selected to the area under the brush. To select a new texture to paint, make sure you are in landscape painting mode, then under the Target Layers section, select which texture you want to paint with by clicking on it in the list. Whichever texture is highlighted will be painted on the landscape. In the image below, you can see the soil layer is highlighted, meaning that this is the texture that will be painted to the landscape. When you first start painting on your landscape, you might run into an issue where the base material disappears or turns black, like in the following picture. This happens when there is no paint layer data on the landscape when you first start to paint. To fix this issue, continue to paint over the landscape, generating the paint layer data as you go. If you would like to fill in the entire landscape, first select a large brush size, like 8192.0. Pick a layer that you want to use as a base and paint over the entire landscape once. This will create paint layer data and allow you to continue to paint without anything turning black. Another issue that you might run into is that the scale of the textures on your landscape are either too big or too small. To fix this, open your landscape material and select the Landscape Chords node. With that node selected, adjust the mapping scale in the Details panel and save the material. Once the material is recompiled, check the scale out in the viewport. If the scale is not to your liking, then repeat the processes above until you get the results you want. Here is a comparison between a mapping scale of 0.5 on the left and 5.0 on the right. Creating holes in your landscape is something that you can do in Manage mode, but only by deleting entire landscape components at a time. To get around this, you can use a landscape hole material to mask out the visibility and collision of a certain location on your landscape. This is great if you want to make something like an entrance to a cave in the side of a mountain. You can use the same material for your landscape material and your landscape hole material. But be aware that materials that use opacity masks are more costly performance-wise, than materials that do not. This is why you have the option of creating a separate landscape hole material. Find the landscape material that you want to use in the content browser. So create a duplicate of original landscape material. And name it Landscape Material Hole. Now open the material editor, and in the Details panel set the blend mode to masked. Please note the original landscape material has opaque in blend mode. Whereas in hole material it's masked, leading to opacity mask is active. So the difference is the opacity and masking. Rest everything remains the same. Now search for Landscape Visibility Mask in the search palette. Next, add the Landscape Visibility Mask node to the material graph and connect its output to the Opacity Mask input. The visibility tool is used with a landscape material that has been set up to use a landscape visibility mask. This enables parts of the landscape to be painted invisible or visible so that you can create caves and other underground areas using additional static mesh actors. This demonstration shows painting the invisibility and then repainting the visibility. Let's check the inputs. With left-click, this adds the visibility mask, making the landscape invisible. And with Shift plus left-click, this removes the visibility mask, making the landscape components visible again. Once the material has been compiled, it is now time to assign it to the landscape so that it can be used. This can be done in the Landscape Hole Material section in the Details panel. Now you can set up the rest of your landscape material like you normally would, and when completed, you should have something that looks similar to this. You should now be able to mask and unmask the visibility of your terrain. After creating a material for a landscape hole material, you need to assign the material to a landscape actor in your level to use the material. Select the landscape, either in the viewport or in the world outliner. In the Level Editor's Details panel for the landscape, in the Landscape section, next to Landscape Material, click the Assign arrow to assign the selected material. Here in this example it's already selected. Now assign the landscape hole material to a landscape. You can assign different material to act as the landscape hole material, which is a material with specific opacity settings. Find the landscape hole material that you want to use in the content browser and select it. Select the landscape, either in the viewport or in the world outliner. Navigate to the Level Editor Details of Landscape. Under Advanced, get the landscape hole material. Select the arrow to assign the selected material. After you have set up your landscape hole material, you can use the painting tools to create a hole in your landscape. In the Landscape toolbar, in Sculpt mode, select the Visibility tool. Find the location on your landscape where you want to create a hole. Adjust the brush size to the size you want to use. Left-click to create the hole and Shift plus left-click to erase a hole that was created. Every other layer works the same when used for painting. You can now fit static mesh actors in the hole in the landscape to create a cave. Hope from this video, you will start to move into building in more advanced mechanics, in an easy-to-follow step-by-step approach, which will allow you to play around and build your own content, to eventually build your own game. Thanks a lot, see you in the next video.